Alright, so we're going to begin this chapter by just quickly reviewing what limits are. And this goes all the way back to chapter 3 on page 212. So if you want to take a look in your textbook about it and just kind of glance over examples and what we did back then to refresh your memory. I'm just going to do a quick recap in the example in the next slide. But remember, what we're saying is we would have to look at what y was doing. That's what the limit is asking us. What is our function? What is y doing as x approaches a certain value? And we use what we call direct substitution, unless when we directly substituted in, it was undefined. When that happened, we had these three different means down here to try to get it so that we could get a defined answer. And if not, then we would just say, alright, then the limit does not exist. So here is some examples on what we were looking at. So the first step is always to try to figure out if we can directly substitute in. So when you do that, you could take this 3 and substitute it into our function. But what I hope you will see right off the bat is this right here will get us an undefined. So we would have to explore those 3 different methods. Being that they're not new to us anymore, I'm just going to say right now, this is an example of something that we would have to divide out or factor out. So I'm going to rewrite this, and this is where we would have a removable discontinuity. And what I've done is I've reduced this now to studying the equivalent function x plus 2, and now I could go ahead and just sub this in. The limit of this function, x squared plus x minus 6 over x minus 3, would just be 5. For something like this, we would have to explore those different methods again of trying to, because if you plug this 2 in, we're going to get an undefined. So we're really trying to get rid of this factor on the bottom. Can we do it? And what you're going to find out is maybe yes or no, depending on can you rationalize that problem or not. The other thing down here, what we have is a fraction within a fraction. So can you condense that? If you want to, I can kind of review those in class if you want to do that during your work time. So what are we doing with limits this time around? Well, we're going to be using these limits now to study horizontal asymptotes. So one of our key definitions of this chapter is, of course, a horizontal asymptote. And the key word here, I've underlined it and bolded it, we're looking at end behaviors. Because in the past, what we've known asymptotes to be is a line that can never be crossed. And this is true, but we're only looking when the end behaviors do not cross. So it's possible that somewhere in the middle, our function might cross this horizontal line that we call an asymptote, but the end behaviors will never cross this line. So what are they approaching? And that's the horizontal asymptote. I do just want to go into a quick review, or just a quick connection. Last year, when we were doing end behaviors, we would look at a function or a graph that looked something like this. Right? And I would be asking you, and remember, last year we had like these little smiley faces on them, and I would ask you, is this a function that's even or odd? And we would also ask, is this a positive or a negative overall function? And when we were looking at these, then we would specify what are the end behaviors doing. And how I actually told you to write them was, as x approaches, let's say, positive infinity, then y in this case, for the problem like this, we would say, well, y approaches, and then positive infinity as well, because it's shooting up. Alright, otherwise, as x approaches negative infinity, so as we're going towards the negative direction, we're going to say that y is approaching, and then, in this case, negative infinity, because it's going down. It's getting smaller and smaller. So last year, this was how I had you study end behaviors, because we had not been introduced to limits yet. But now what we're going to be saying is, this is basically the equivalent to this up here. What we're saying is, alright, as x is approaching positive infinity, what is our function doing? And it's going to be, in this case, approaching infinity. Same thing here, as x approaches negative infinity, that's associated with this limit now. What we're doing is we're studying what the y values are approaching as x goes off in the positive and negative direction. Okay, so we're studying the end behaviors here. Okay, so to study this idea of end behaviors and horizontal asymptote, what I'm going to ask you to consider is number 1, and we're just going to study looking at a function and the end behaviors. And in order to really follow along, you need to open your books to page 352. But what I'm going to help you do right now is decide what are the end behaviors of this function. So our old way of doing this, and I will be showing you a shortcut here in a moment, but what we would consider is as x approaches infinity, because this would tell us what our right end behavior is doing. In the graph, as we're going farther and farther in this direction, what is y doing? So that's up in the air. It's a question mark for right now. So I am going to just complete and copy out a chart, and I'm going to fill in some x values that are decently large. So I'm going to start with 100. I'm going to get larger, 1,000. And we're going to see what is y doing as these x values are getting larger and larger. So I am just going to plug them straight in for my x. I'm going to input those in. So just typing them into the calculator, what I get is 2.99. When I type it in, 4. I hope you get the picture. You can check my work if you want. But last year, how we would have written this was as x approaches infinity, y is approaching, and then we could say 3. It's getting closer and closer to 3. How we're learning it this year is the limit of 3x squared divided by x squared plus 2. As x approaches infinity, what we would say is equal to 3. They're saying the exact same things. You're going to have to consider both end behaviors. So now as x approaches, you could plug in negative 100, and then negative 1,000. And negative 10,000, you're going to get the same exact result, ... So basically, as x approaches negative infinity, once again, y still is going to be approaching 3. So another way to write this, and how we are going to start looking at it, is the limit as x approaches, and then negative infinity. Our function, or our f of x, is equal to 3. In this case. So those are our two end behaviors. What this is saying is some sort of horizontal asymptote at y is equal to 3, because that's what you've determined, or that our end behaviors are approaching 3. And it's going to be looking something, and it is approaching it from the bottom, so I'm not really sure if this is going to actually be it. But I mean, it's something to the point where your end behaviors are getting leveled off at around 3. Okay, so I just have a couple more definitions left to do, and then we'll be done with this lesson. But I just want you to consider this, because I am going to be introducing a shortcut to you soon in determining horizontal asymptotes, so that you don't have to do when x approaches infinity, so you're plugging in larger and larger values, and then determining what the y's are, so that you don't have to do those charts every time. So I just want you to keep in mind, if I were to take this entire top and multiply it by 1 over x squared, then as long as I did that to the bottom, I'd be okay, right? So I would just have to multiply everything by 1 over x squared on the bottom as well, because keep in mind what this is equal to is just equal to 1. So I haven't changed the value of this function whatsoever. I've just multiplied this entire function by 1. But it will change the look, so we get an equivalent function. What we're going to get is 3 times x squared times x squared. So just multiply straight across the tops, multiply straight across the bottoms. What we get is x squared on the bottom. Alright, all over. And then we're going to take this and distribute it to each one of these terms. So we're going to get x squared all over x squared. Alright, and then plus, and we're going to get 2 over x squared. Okay, and what we're eventually going to be doing is canceling out any kind of like terms. These are going to become just 1 over 1. So what we're going to get is at the top 3 over, and then 1 plus 2 over x squared. Alright, I just want you to consider that, because this right here is equivalent to this right here. I know I'm kind of jumping all over with some ideas here, but what I hope in the next slide is that we bring it together. The the previous slide to this one and this property, I hope you can really bring together in order to now calculate your horizontal asymptotes. Is if we were to take the limit of these of some sort of constant over some sort of power of x, what's going to happen is it's going to be equal to 0. Consider it like this. If I had the limit of 3 over x to the second, for instance, as x approaches infinity, well, this x, if we could directly substitute in infinity, that's a huge number. It's 3 over a huge number. So if you have 3 over 1 zillion, think about how small that number is. And if we could actually put infinity in there, if we could actually do this, which calculus to a point allows us to do, then so it's going to be some small number. It's essentially 0. We're going to start with number 13, and I'm going to do 13b just so you can really see how the last few slides in the PowerPoint apply. So you're going to be using this idea of modifying the overall function so that it's more telling to you by kind of reducing it down. And then we're going to be studying what is the limit doing by actually using your property of 5.5. So for number 13, they have it a little bit weirdly set up, but I'm going to, they said find the limit as x approaches infinity of h of x, and they kind of make you plug a function into this to figure out what you're solving for. So I'm just going to write it out for you as it should be. Okay, so that's the setup that I'm trying to solve for. And what I am going to go ahead and do is I'm going to note that on the bottom, my highest power, the only power, is x cubed. So I am going to divide the top by x cubed and the bottom by x cubed, which would be the same thing as multiplying the top by the reciprocal. So I'm going to just multiply everything by 1 over x cubed. So essentially what I'm doing is going to take every single one of those terms on top, divide it by x cubed, and this term on bottom, and divide it by x cubed. So what I will get is this: 5x cubed divided by x cubed minus 3x squared divided by x cubed plus 10 over x cubed all over x cubed divided by x cubed. And you might not think this tells a whole lot, but you'll see the magic of this. So we have the limit as x approaches infinity. These guys are going to cancel each other out, so what I get left is 5 minus these guys are going to cancel each other out, but I get 1x left out on the bottom, so I just get 3 times 1 on top, so 3 over x, and then plus 10 over x cubed because nothing cancels each other out there, and then on the bottom I just get 1. So this is now the limit. I'm looking at it. Keep in mind this function is equivalent to the function of study before, but now what I can do is I can apply the fact that this limit is going to be going towards each one of these terms separately. So please do review your properties of limits, but you could look at it like this. And what I hope you can see now is this piece right here, properties of limits, once again, is just equal to 5. This piece right here, that's the property that we just learned in this section, that's just equal to 0. If you could plug in infinity in for this x, basically what this function would be doing, it would be 3 over a huge number, so it's basically 0. Same thing with this last piece right here. If you could plug in infinity on this bottom, what would happen is you would get 10 over infinity cubed, so essentially 0. And so what our final answer amounts to being is the limit of this function is just equal to 5. Alright, so before how we would write this was as x approaches infinity, right, y approached 5. But now what we can look at this is, or this as, it would be the same thing as saying the limit of our h of x in this case. As x approached infinity, we're saying that it was equal to 5. Oh, yeah, my startboard's being weird. That's a 5. Alright.